Okay, so the second presentation will be given by Professor Junwei Zhao. Zhao Junwei received the master degree in School of Automotive Engineering, Chang'an University, Shanxi, China, in 2020. He is currently purchasing the doctor degree in School of Transportation Science and Engineering, Beihang University. His research focuses on additive load spectrum of hybrid transmission system under comprehensive driving cycles.
Yeah. Thank you. Yeah. Good morning, Pro-Xu. Good morning, everyone. I'm Junwei Zhao from Beihang University. I'm glad to have the opportunity to make this presentation. So today's my research topic is research on adding road load spectrum of hybrid transmission system under comprehensive driving cycles. Now let's start. As we all know, the transmission is a complex assembly, and the hybrid transmission consists of many parts, including motor, clutch, shift element, transmission shift, gear, and bearing. And the failure of any commuter will directly affect the reliability of the transmission. Throughout the life of the transmission, parts are subjected to different forces in different working modes. So, how to improve transmission life and adaptability to driving cycles? By accurately predicting the load cycle of the parts, and the reliability of the parts is verified by loading tests. Furthermore, we can effectively analyze the failure reason of parts source through designing optometry and structure material optimization to improve transmission reliability and durability. Next, the configuration of the hybrid transmission system is shown in figure, which is power split DHT and is composed of an ICE and two more electric motors, EM1 and EM2. In addition, the DHT can release the switching of different working modes through the clutch C1, B1, and one-way clutch to meet the power demand at different speeds. The DHT has 5 types of working mode, respectively EV1, EV2, PS1, PS2, and ECVT, which can be adopted under the appropriate driving cycles and loads to improve the fuel economy, as shown in table. In addition, since the motor power is reversible and its torque can be negative, the motor can not only be used as a reducer to replace or supplement mechanical braking, so negative torque of the wheel and can also be transmitted to the DHT. In addition, we adopted the specification of the vehicle shown in table. The first step of designing load spectrum is to determine the working mode of DHT under different driving cycles. In the paper, dynamic programming algorithm is selected as the global autonomy control strategy. Through the backward simulation calculation and the forward optimization calculation, and set minimal fuel consumption as the objective function source, the optimal operating model of the DHT under a given driving cycles is important. So for the data process, we can obtain the distribution of wheel and torque at different vehicle speeds and different working modes. At the same time, working time and per person are also important. However, the load distribution of the wheel and torque under only one driving cycle segment doesn't reflect the actual situation. Only by analyzing different driving cycles as far as possible convey or obtain a comprehensive and accurate view and tackle distribution. In the paper, 13 different types of driving cycles were selected to develop an accurate experimental load spectrum. In order to further determining the characteristics of different driving cycles, we use the value of CV for driving cycles clustering. The 13 driving cycles are clustered as 5 driving cycles, including highway, monotonous, high dynamic, standard, and urban driving cycles. The load spectrum editing process is shown in the figure. Step 1. Extracting and managing the wheel and load distribution of different working modes, corresponding to different driving cycles, and obtain the wheel and load distribution data of 5 working modes of the DHT corresponding to the time history under the comprehensive driving cycles. Step 2. Compressing the load time history of different working modes under comprehensive driving cycles, removing the points with the same load value at the adjacent position in the load history, rating effective load data, and then removing no-peak and no-valley values in the load history from the effective load data to ensure that for consecutive data points are peak and valley data. Step 3. Conducting the refollow counting on the load distribution process by the 4-point cycle counting method, aborting the from to refollow metric corresponding to different working modes after refollow counting process, and extracting the refollow from quizzing histogram under the load time history of each working mode. Step 4. Using the reflow metric exploration method to explorating the amplitude and from quizzing in both directions, fitting the amplitude distribution of the refollow metric and aborting an estimate of Weber's no pre-metric distribution. Step 5. According to the extrapolation results of refollow metric, removing low amplitude load distribution transformer in the continuous statistical load into an at-level load spectrum, and aborting the experimental load spectrum, which can be finally loaded on the commutes. The load distribution before and after as shown in the figure. Next, as shown in the picture, the load circulation distribution on the different working modes corresponds to the comprehensive driving cycles. The complete load closure history and the corresponding frequency releasing in actual driving cycles can be easily seen, providing the original load spectrum for subsequent load spectrum extrapolation. As shown in the upper right corner, we can see that the data load distribution from peak to valley values in EV1 mode and the corresponding load frequency according to the regulators of load distribution, we can carry out further data treatment. Next. The extrapolation of refollow metric is a no-pre-metric extrapolation method, which constructs a probability density function of frequency distribution according to each load cycle element, and the extrapolated refollow metric is constructed by means of random cycle number according to the probability distribution. Taking EV1 working mode as an example, by extrapolating the original load spectrum, it can be concluded that the amplitude of refollow metric obeys Weber's distribution, and the means obeys the normal distribution, as shown in figure. The above figure shows the accurate distribution results of the EV1 amplitude exploration. Since random numbers were used in the amplitude extrapolation process, some values may excite the actual situation. So, the boundary value of the experimental load spectrum was 1.5 times of the maximal value of the original load spectrum. The figure below shows the frequency distribution cover of the EV1 amplitude extrapolation load, and the overall trend is consistent with the original load spectrum. According to the at-level load spectrum classification method, the continuous load spectrum can be converted into a fixed load spectrum, which is easy to control in the process of batch test. The extrapolation load distribution of EV1 mode is shown in table. It can be said the extrapolation load distribution that the frequency of low amplitude load distribution is 368,948 times, accounting for 78.83 percentage. But the low amplitude load distribution has little damage to components. Therefore, it's necessary for further aborting the experimental load spectrum that can be loaded on the batch. Ordinary practice for dealing with low amplitude loads include a variety of approach. The method that we use is removing low loads of less than 10% of the maximum load. Table shows the experimental load spectrum corresponding to different modes. Under comprehensive driving cycles, taking EV1 working mode as an example, the load spectrum ranges from 408.63 Nm to 3,269 Nm, and then the load distribution of the components involved in EV1 working mode can be analyzed based on the target cumulative frequency of 1 million times. The total cycle time after refollow metric extrapolated 612 and 98 hours left, saving 427 hours. Thus improve the experimental efficiency and reduce the test cost. Finally, make a summary of this paper. The paper mainly focuses on the designing and analyzing of load spectrum process, including original load spectrum, stressing load spectrum, experimental load spectrum, and design load spectrum. And then the experimental load spectrum important is the load spectrum of the wheel and the tackle. According to the energy follow transfer path of the hybrid transmission system, the designing load spectrum of each component is determined. Thank you. That concludes my presentation.
Okay, thanks for the very detailed and very solid work on this added loading load spectrum analysis for the hybrid transmission system. And are there any questions to Mr. Zhao? Okay.
In your opinion, how to obtain a more accurate load spectrum, and what are the key points affecting the design of another spectrum?
Okay. I think if you need more accurate designing load spectrum, I think you need more accurate actual driving cycles of the vehicle speed as a reference. On the other hand, you need a more accurate physical model so that you can obtain more accurate designing load spectrum.
Thank you.
Okay, I have just one question. I noticed that in the presentation, the rain flow diagram or rain flow mode seems to be a very important part of the analysis. So could you explain to us once again, of this meaning? So the x-axis or y-axis of the physical meaning of this rain flow diagram.
This is a data process method. Just rating
So what's
effective
the meaning
data.
of the mean value of the load and also the amplitude of the load? So especially on of the amplitude of the load. So
amplitude
yeah.
Classified as 8 level load spectrum. Continuous load spectrum converted into fixed load spectrum.
Okay.
Okay, thank you.
Okay. So, any questions?